Good morning, ladies and gentlemen. We,
Niklas Wendel,
and Tillmann Hofbauer,
and me, Luisa Gerhardt, are a group of space enthusiastic students, and we're happy and excited to talk about our project here in front of you today. In 2009, the active communication satellite Iridium 33 and the inactive satellite Cosmos 2251 accidentally collided. Their fragmentation resulted in the emergence of over 2,000 large debris pieces in LEO, many of which are still in orbit and posing a collision risk to other spacecrafts even today. An uncontrolled accumulation of space debris will have devastating consequences. This was already pointed out as early as 40 years ago, when Donald Kessler warned about the self-enforcing effect of satellite collisions. The debris pieces produced in the collisions can collide with other satellites or objects, thus starting an unstoppable, cascading chain reaction. This scenario would obliterate all future spaceflight opportunities. At this moment, more than 1,700 uncontrollable debris objects with high fragmentation risk, so possible targets for deorbiting, are orbiting Earth in LEO, meaning that collisions like the one between Iridium and Cosmos may occur frequently in the future. This immense quantity makes one thing very clear. The spaceflight sector is in critical need of a safe, scalable, and cost-efficient solution for the debris problem. By basing our approach on small satellite technology, we are confident to present a solution meeting those three requirements at once. Using a small satellite as basis for developing an active debris deorbiting mechanism, a problem caused by fundamental physical principles directly comes to mind. How can a small satellite dissipate enough orbital energy to deorbit a much bigger and heavier target? Instead of using chemical propellant, the approach we took while engineering our probe DEBRIS, which stands for Deorbiting Broken Stuff in Space, is using passive deorbiting techniques to harvest the required energy. Weighing 40 kilograms and fitting into 1/5 of an ESPA slot, the debris probe will feature both an electrodynamic tether of 300-meter length and a drag sail with a surface of 40 square meters. These dimensions represent the result of a complex optimization calculation, taking into account the very different deorbit characteristics of both devices. The chosen system envelope of the DEBRIS probe will allow us to deorbit a large quantity of debris objects in a reasonable time span. It is important for the flexible use of the DEBRIS probe that it can be taken to space by a variety of carrier rockets. After being ejected by the carrier rocket, DEBRIS will have to perform an orbit transfer to the target's orbit. We were originally planning on using a 22-Newton bipropellant thruster for orbit transfer, as well as smaller bipropellant thrusters for relative maneuvering, so solely chemical propulsion system. After some research in the area of ion engines, we are now evaluating electrical propulsion for orbit transfer. With the latest design iteration, the DEBRIS probe will be able to reach orbit heights from 350 to 2,000 kilometers and carry out an inclination change in a scale of 1 to 3 degrees.
As soon as we are close to the target at approximately 3,500 meters distance, we start the search for the target. For this, we use the radar on board of DEBRIS probe. At approximately 3,000 meters distance, we finally found the target. From now on, we can close in iteratively to the target and and shrink the distance every step. It is important to note that the maneuver we are using here is stable, so in case of engine failure or communication failure, there will be no risk of colliding with the target. At an orbit of a minimum distance from 25 meters and a maximum distance of 75 meters, we start our target mapping. For this, we use the high-resolution data from the LiDAR and the camera to gather information about the target. At the same orbit, but a bit later, we do our go, no-go decision on capturing. This does not only include whether we do capturing, but also how we do capturing. For this, we need detailed information on the target. Therefore, we have the target mapping and remote sensing procedure. For this, we track optical features on the target which are easy to recognize by the cameras on the DEBRIS probe. We then use FPGA accelerated computing to do this in time. we use the LiDAR information, so the distance from the feature points to us, to collect this data. We then send this down to the ground station, where we can derive the shape and the kinematic properties using almost arbitrary computational power.
Great. So let me introduce our capturing mechanism. To perform active debris removal, of course, we will need to be capable to establish a physical connection to the target. But since we are also working on small satellites, we are strictly limited, for example, on power, mass, or volume of the system. Since we reviewed existing approaches to capturing mechanisms, we found none of them really to be suitable for small set applications. Therefore, we want to propose a new capturing mechanism. Our mechanism is slowly based on the ejection of magnetic projectiles, which are connected to aramide probes. The results I'm now going to present to you are calculated using a large physics engine calculation. So we are going to eject our first projectile prior to passing the target on the relative trajectory at a velocity of about 0.1 to 1 meter per second. Later in the process, we of course need to aim the ejection angle. Since the projectile is magnetic, we can do this by using a magnetometer as a secondary application and use magnetic deflection. The precision which is needed is approximately 0.5 degrees. So the final flight path adjustments are then carried out due to the magnetic interaction, since after we pass the target, we can see the first projectile emerging behind the target object and fire several other projectiles towards it. Since all of the ejected projectiles are magnetic, they will attract, resulting in then the connection of both probes and tying a bow around the target satellite. When we now are capable to retract these probes, we can basically pull ourselves in towards the target. We are capable to do this from a distance of over 100 meters. So it's basically reducing or neglecting the need for flight precision on the order of several centimeters, as it would, for example, be the case in case of robotic capturing mechanisms. But let me now sum up what the influence of our DEPRIS probe would be. Of course, we engineered it to be a scalable solution for the stated Kessler syndrome and to prevent the emergence of future space debris belts around Earth. Also, since we used commercial off-the-shelf components and engineered our probe to be used in ride-sharing applications, we can offer fast response times to sudden increases in orbital risks. But looking at a world beyond space debris, we can also see that we are developing key technologies for future orbital servicing activities. Those are especially the remote sensing as well as flight and mapping algorithms, which will be needed for future mapping applications and, for example, orbital refueling. So how's the way towards this future going to look like? That's our first technology demonstration mission, which we plan to carry out in a 6-unit CubeSat. The Detector 1 mission, as we call it, is engineered to demonstrate the novel onboard computing architecture as it was introduced by Tillman. And also it will feature all of the sensor arrays which will be featured in DEPRIS. So the radar, the LiDAR, as well as camera arrays. And of course, we try to mimic the architecture of the future DEPRIS probe using similar components and an identical system architecture to be capable to gather first experience towards the operation of DEPRIS. Looking now at it from a mission perspective, we have the 6-unit technology demonstration, which on the first hand, of course, will give heritage to critical components needed for DEPRIS and orbital servicing applications. But we are planning a mission lifetime of 3 to 5 years for Detector, which will give us the opportunity to use it as an orbital software testbed. Like within the process, we are going to develop, iterate, and optimized algorithms for docking, mapping, and we're going to be capable to use them on real targets in an orbital environment. And also, what's often forgotten, but a crucial point for every active debris removal as well as orbital servicing application is the concept of operations, which is basically the operation of the ground station and procedures streaming data to ground, scheduling contact times to ground stations, and handling the data budgets and human factors within the mission. This is also going to be explored within the detector mission. So, in fact, one could say that the detector is going to pave the way not only for debris, but beyond space debris, also for future orbital surfacing applications. So, thank you very much for your attention. We're glad to hear your questions.
Okay, thank you very much for the presentation. The first set of judges' questions is, what sensors are used to determine if the pairs of magnets have connected properly on the far side of the target satellite?
We can measure this by the force on the rope on the one hand, and also by our movement. So at least once we are once we are tightening in the rope and it becomes more and more smaller, we will finally hit the target if it works, and then measure, okay, that's some force and we are moving. If this is not the case, the magnets would move around the target, and we would suck them in again and could restart the capturing process.
Okay. Next question is, let's see. How would you counteract the thrust effects of shooting the gas pressured projectiles? And how would you retract, I think you touched a little bit on this, how would you retract multiple cables to avoid starting a tumble on the primary spacecraft?
So, yes, for the first part, we currently are evaluating projectiles with a weight of approximately 4 grams and flying a satellite of 40 kilograms. The impulse is quite low, while we also have thrusters for relative maneuvering on the order of thrust levels of 0.2 newtons. So we can thrust on that, as well as in the picture you right now have on your screen, you can see 2 batteries of magnet ejections. And on the other side of the rope are the same 2 batteries, which basically displays that it's a symmetric symmetric setup. So retracting the ropes, of course, we also always eject at first one rope on the one side of the satellite and then use the rope on the other side of the satellite. So we can retract simultaneously without going into a tumble motion.
Okay. Let's see, next question would be, what are the largest risks for unintended contact and generation of debris during the rendezvous or capture process? I believe the, safe ingress, safe egress, and how would you mitigate those?
So because our capturing mechanism makes sure that we can capture the target while it's still very far away from us, and then tuck in the ropes in a way we can control, we can make sure that there will be no rendezvous with the target before we want the capturing to begin. And also the shown atom maneuver, we are flying around the target, make sure that we can control in every stage where we are orbiting the target, we can make sure that we don't get too close to the target.
Okay, and then just to add on to that, as you've done your rendezvous, are you looking at passive abort trajectories in case, I'd imagine most of the subsystems OBCs are single string, and if there was a fault during a critical operation, have you looked at the passive abort trajectories for the mission?
Yes, so the basically our relative maneuvering is based on the Clohessy-Whiteshaw equations. And so we are first performing our bar hops, which are passive in itself, that so integrating over time, we would have passive aborts due to the drift in orbital inclination over time, which will affect us probably less than the target, since the target is heavier, and therefore our inclination will change, and the passive abort goes into an inclination change while still circling on the R-bar of trajectory.
Okay. Thank you very much for your presentation, and appreciate the time today. That concludes the presentation.
Thank you.